We will learn in this chapter a number of methods used to design beams, and what we find is in the previous chapters that we're able to calculate the stresses uh, on any beam or any cross section, going from a straight beam to a curved beam to any kind of configuration. So we are doing very well as far as the stress is concerned. However, as we will see when we apply these methods to designing power transmission, that the power transmission shaft itself is considered a beam, and the beam and the shaft has different cross sections, so it's not all uniform because you have to attach gears, for example, um, and bearings, and therefore we need to also be able to design such shafts for given deflections that are imposed on the shafts, or for maximum amount of slope of the shaft so that it can fit into various design applications. And therefore, beam deflection slopes of the beam itself, the line slope, and also the energy, elastic energy that is stored in the beam would be important topics. They're all connected together. Finally, in this chapter, as we will see that one type of very dangerous deflection is due to buckling. So if I have a very long and skinny beam and then I apply an axial load, there is a possibility that the beam is unstable, and then it will go into a buckled configuration that has very large deflection. So the chapter is basically to allow us to design for a range of conditions related to deflection, slope, energy stored, and also to prevent buckling condition. So we'll see here that if you look at the chapter, we will start working on defining the spring rate for a beam, and the spring rate can be for a simple tension member or a bent member or any kind of configuration. And then we will focus on the deflection due to bending, and we discuss several methods used for beam calculations of beam deflection. But because there's so many different methods and we have limited time in the course to go through some of them, we will focus on two methods. One that is based on singularity functions, as we have discussed that in chapter 3. And another method that is based on energy storage, and this energy storage idea is called Castigliano's theorem. So with this theorem, it allows us to compute deflection of beams of indeterminate support system. As some of you know, beams can be called determinate or indeterminate. If a beam is a determinate beam, it means that the number of equations are sufficient, equilibrium equations are sufficient to determine the reactions on the beam. However, if the number of reactions is greater than the number of force equilibrium equation, force and moment equilibrium equations, then the beam is called indeterminate, and we need to consider displacements as well as force equilibrium. And Castigliano's theorem allows us to calculate deflections of indeterminate beams as well. We will then move on to study curved beams using also Castigliano's theorem, and then we will kind of move on to look at elastic stability and buckling and shock and impact effects on beams. So all of these things are kind of connected, and we will start this series of lectures on beam bending today with the simple introduction of spring rates and calculations of simple deflections of determinate beams. So I'll look here at the first topic. And the first topic here, you can see that we can consider a beam as a spring. So the beam can be considered can look as a linear spring. If we apply a force in the middle, then the deflection under the force, for example, if you measure that deflection under the force, this deflection, you can call it y. As the force increases, then y will increase. If the rate of increase is proportional, then you get a straight line, and then the beam is called a linear spring, or the beam can be considered as a linear spring. However, in some situations, the beam, when you apply a force, then the deflection y is nonlinear, so it doesn't go proportional to, the y doesn't go proportional to the force, and therefore the spring rate, which is the slope, the spring rate is dF by dy. This is spring rate, we can call it the spring constant K. In the linear spring, it's constant indeed, but in a nonlinear spring here, K is a function of y, and here also K is a function of y. So these cases can be linearized stepwise, but our work in this section here will be just based on linear springs. So let's start from the beginning to define what is the spring rate. The spring rate, as we mentioned, the rate of change of the force with respect to the displacement under the force, and therefore if we have the displacement proportional to the force, then you get a constant, and this constant is the spring rate constant, and the units are Newton per meter. So Newton meter minus 1 is the spring rate constant. Now, if we look at application of this previous formula to something very simple, and let's take a simple beam, like for example, the beam is considered an axially loaded member, like this case. So if I have a force loaded on this axial member, and the axial member has a cross-sectional area A, and it has an elastic modulus E, which is, we call it Young's modulus. Then we know that delta L over L is the strain, and the strain is equal to the stress sigma divided by the elastic constant. So this is the basic relationship between the stress and strain, and the stress is the force divided by the cross-sectional area. So we get delta L over L equals to F divided by A times E, and therefore delta L would be equal to F times L divided by AE. And this is kind of the relationship that is given here in equation 4.3, where delta is the delta L, and it is linearly proportional to the force and the length of the axial member, and inversely proportional to the area and the elastic constant. So the spring rate is the force divided by delta, so we can rearrange this equation, and therefore we will get a new kind of relationship, and this relationship is that K is equal to A times E over L, and that's the spring constant for an axially loaded member. Note that if we go to another member, for example, the next example that we will see will be for a torsional type loading we'll find that, as we will see that in the next example, that if we consider torsion, for example, this is a cylinder, and then I'm applying a torque. When I apply the torque, as the torque increases, then the angle of a twist will increase. The torque will induce an angle of twist. If the angle of twist is proportional to the torque, we will consider this also as a torsional spring, because if we release, then we get a force that can lead to an oscillation, for example. So we could use this as a torsional spring. So that's another type of spring that we would consider. A third type is that if we have a beam, a horizontal like that, and then you're applying a load in the middle, and then you're supporting from the two ends, then under that load you will get displacement, and therefore you can consider a transversely loaded beam as a spring. So a spring can be axially loaded, transversely loaded, or torsionally loaded member. So let's look at the torsion case next. And the torsion case here will show from chapter 3 that the angle, torsional angle or twist angle per unit length is T over Gj. Gj, we called it the torsional stiffness, and therefore this is per unit length. Then if we want to have the total angle of twist, we multiply by the length of the torqued member. Here in equation 4.6 is the same as equation 4.5, but we just converted the angle to degrees, and we substituted for the J, which is the polar moment of inertia of the round cross section with a diameter d, to give us kind of more of a practical calculation of the angle of twist in degrees. So this is in degrees. So if I'm looking at the torsional spring constant for a round bar, it is the relationship T over theta, and that gives me Gj over L. And as you can see here, the torsional spring will be stiff if the product of G and J is very high. So next we move on to kind of the core subject of this part of the lectures, and the core subject is the deflection of beams of variety of support systems and loading conditions. Why are we doing that? Because the subject matter is power transmission shafting, design of the shaft, and the shaft will be considered as a beam that has forces that come from gear systems or from pulleys or flywheels, and therefore we need to calculate the deflection. So the basic idea for beam deflection is that the radius of curvature, when you apply a moment on a beam, then the radius of curvature is going to, as the moment increases, then the radius of curvature will decrease. So if we consider the curvature itself, curvature kappa is the inverse of the radius of curvature, then we can say that the curvature of the beam is proportional to the applied moment. And that's what we have here in this equation here. So in this equation, we have the curvature, and the curvature is kappa, and kappa is 1 over rho. Rho is the radius curvature, and that is equal to m over EI. So this is from kinematics. The kinematics is the beam kind of bends in a circle, basically. This is a kinematic assumption. We assume that the beam would bend as a part of a circle. and we find that the proportionality constant is 1 over EI. The product of E times I is the rigidity, flexural rigidity of the beam. However, the curvature from mathematics is equal to the second derivative of the curve that constitutes the beam axis divided by a factor that we've known from our calculus a long time ago, that is 1 plus the first derivative to the squared, and all of that is to 3/2. So if we look at this equation here, this is the curvature, and for very small slope, meaning dy by dx is very small, then we can ignore the influence of the first derivative compared to unity. It would be very, very small. And then we end up with an easier formula to discuss, and that is the second derivative of the deflection curve is proportional to the moment, and the proportionality constant is 1 over EI. And then if we also think about, we have a line, a beam line like this going, if we take the slope of this line, then the slope, this is the angle here, theta, the angle theta will be the first derivative of the deflection curve with respect to x. So these are the principles that we will use. So let's see how we're going to use that in calculations of beam deflection. The first equation that we have learned from the previous chapter is that the transverse shear force, V, is the first derivative of the moment with respect to x, and then the applied force, Q, which should be Q is a function of x, a distributed force on the beam, and is taken to be in the upward, positive meaning in the upward direction. So this Q is equal to dV by dx. And therefore we see that right away that we have a successive set of differential operations. The second derivative of the curve is equal to m over EI. This is from kinematics. And then equilibrium will give us these two equations. And the equilibrium tells us that the third derivative now of the deflection curve is V over EI, and the fourth derivative is Q over EI. So the procedure is that in general, we start with the distribution of Q, and that could be like point forces or distributed loading. And we can also have moments distributed, so that's another complication. But let's say if we have Q, then we would integrate once, we would get the shear force distribution as a function of x, integrate another time, and that will give us the moment distribution. And then if we take the moment distribution and divide it by EI, we will get the curvature of the beam. So we would know the curvature as a function of x. Now the curvature, if we integrated 2 times with the boundary conditions that are applied, we are able to compute the deflection of the beam at any point. So I'm going to stop the lecture here, and then we'll start on the next segment to look at specific examples of how we're going to follow this procedure. We'll see you next time.